So we sort of talked about this really early on in class. We were talking about the difference between accuracy and precision. And that's sort of be touching on what we're doing today. And so I put this in out of order because I think it's important that, more and more we do experiments, the more and more we're going to be collecting data. You're going to be getting observations, you're going to be recording things, you're going to be measuring masses, you're going to be measuring volumes. And it's important to know what's the meaning behind uncertainty? What's the meaning behind experimental error? Because there's literally no way to avoid experimental error. There's just going to be some. What we try and do as chemists and as scientists is try and limit the amount of error as much as we possibly can. So if we know what the ranges of experimental error we can predict, then we can know how accurate or how precise our measurements really are. Because if you have a hypothesis and you do an experiment to test it, you really can't prove or disprove that hypothesis without some indication of how accurate your results are, right? So if you predict some reaction is going to give you 25 grams of precipitate, and you measure out 35 grams of precipitate, then you might say to yourself, well, that disproves my hypothesis. Well, no, it doesn't really, unless you know exactly what the precision in that measurement is. If you set up your experiment in such a way that the answer could be plus or minus 10 from 25, then you're well within that error. And I would probably tell you to make yourself a different set of experimental conditions to lower that error. But you wouldn't be able to disprove anything if your answer was within the experimental error. So what we try and do is get that experimental error as small as possible. So we're going to basically use all these different methods of measuring. We're going to use different pieces of equipment and see the precision and the accuracy and the uncertainty, because it's the uncertainty that's really key here. If we know going in what the uncertainty is associated with the measurements from different pieces of equipment that we use, then we would use either different equipment to lower our uncertainty, which would be the best way to go forward. Or if we would be able to prove ourselves plus or minus the uncertainty in our measurements, then we really don't need to do another experiment. So we're going to determine the uncertainty of measurements with these standard things and determine the accuracy. And we'll see that they're related to each other, but they're not exactly the same thing. So you're probably familiar with our graduated cylinder here, and familiar with how to make measurements with it. But we probably don't know enough to say how precise or how uncertain we are about the exact volume when we measure something. So it's important to realize what these marks on the graduated cylinder and our other pieces of glassware actually mean. So you're probably aware of what a meniscus is, right? When you pour something into a cylinder, we learned today in class that water is polar. And one of the things that polar liquids do is they stick to each other quite tightly, because there's a slight negative charge and there's a slight positive charge in a polar molecule. And they stick together so tightly that they actually pull each other up the sides of a narrow channel. And so we need to measure from the bottom of that little curvature in the liquid. the less and less polar something is, the less and less this meniscus is. Something like benzene or octane or something that's really nonpolar would just be flat all the way across because there's not that same amount of molecules pulling on each other. So getting back to measurements, if we were to try and figure out what's the actual volume in here, what would people say is the actual volume represented by the blue liquid? I don't all yell at once.
6.75.
Okay. So you're saying that because you think to you, it looks like the meniscus is about halfway between 6.7 and 6.8, right? Mils?
Yep.
That seems reasonable. So each one of those, so the big checks, the large lines are 1 mil increments, so 6, 7, 8, 9, 10. And there's 10 smaller lines in between each one, which is 1/10 of a mil. And so, yeah, that wouldn't be a bad, because remember, the third digit in any measurement of volume is an estimate. So we know by looking at this that it's more than 6.7. That meniscus is a little higher than the 6.7 line. And we can clearly see that it doesn't come up to the 6.8 line. And so we know it's more than 6.7. We know it's less than 6.8. So you need to estimate what the third digit is. And so we have an estimate of 5. Somebody else may have said 6.74. Somebody else may have said 6.76 or 6.77 or 6.73. Those are all acceptable because it's up to each one of us to sort of gauge what we see. Nobody else can tell you what it is you're seeing. But what we need to understand is, what is the uncertainty in that measurement? Because obviously there is some uncertainty. Someone else may have given a different number. And so since this particular number is an estimate, we need to know what the levels of uncertainty there are in that estimate. So we can present this number. If we were like writing a paper, for instance, we would give a result of some sort of measurement, and then we would say plus or minus some amount. This plus or minus is the uncertainty. And a measurement without any uncertainty is pretty useless. We get some amount of uncertainty from just the number of significant digits. That tells us that there's uncertainty to the next digit and that the best we could do is 0.5. But that doesn't really tell us the amount of uncertainty in that number. And so we're going to figure out exactly how to do that in today's lab. Whoop. There we go. So we need to take into consideration, again, oops, damn it, this thing is not cooperating with me today. We need to take into try that again. So we need to take into consideration the accuracy of the measurement we're saying, and we need to know what the precision is of any particular instrument we're using. So we would consider this an instrument. We need to know what the precision is, and the precision is built into, basically is connected to the uncertainty. We need to be able to separate systemic errors or systematic errors and random errors. So a systematic error is the type of error that causes measurements to be inaccurate in a certain way, the same every single day. And the example that they give here is an alarm clock. So if your alarm clock is slow by 5 minutes, that is systematic. that can be dealt with, because if we know that there's a systematic error of 5 minutes and it's 5 minutes slow, then we know exactly how to correct that. We just add 5 minutes and now we have the correct time. But that's not true for everything. Sometimes it's going to be slightly higher or slightly lower, and we're not going to know exactly by how much. That is random error. And random error is basically something that we can't get away from, but we can calculate. So how are we going to calculate random error? Come on, here we go. So relative error is basically expressed as a percentage, and relative error gives you an amount plus and minus. Like there's a certain amount of error we expect when measuring something. And then what's given as the example here is the speedometer in your car. So the speedometer in your car is tested before it ever leaves. Well, it leaves the factory. It's then tested like on a road to make sure that it works properly, and then delivered to the dealer. And so usually it has what's called a tolerance of plus or minus 2%. So if you're driving at 60 miles an hour, it's going to be somewhere in that region of 60 plus 2% of 60 or minus 2% of 60. So in other words, 60 plus or minus 1.6 miles per hour. So if the speedometer says 60, you know that 99% of the time it is going to be accurate to plus or minus 1.6. So if you're not going to really going to get away with a speeding ticket doing 70 in a 65, because the error is only going to be about 2 miles an hour. So you're going to be over by 5 miles an hour. That's well within the error. You're not going to be able to argue your way out of a ticket. If the speed limit is 65 and you're doing 67, you're probably not going to get a ticket, because that's well within the error we would expect for that amount of, for that particular measurement. Let me clear this. Oh, there we go. So systematic error can be corrected for, like I mentioned, if something is running too quickly, something's running too slowly. If your balance, your scale, for some reason, every time you tear it, it goes to 5 grams rather than 0 grams. Well, you can just correct for that by just subtracting 5 grams each time. And then that takes care of the error. But random error, you really can't correct for. What you need is to figure out how big that random error is going to be. And the only way to know what the random error is going to be is by doing measurements, over and over and over and over, and then basically seeing how much variation you get from a specific amount. And so we're going to figure that out for our scale by measuring the mass of a single cup, measuring it over and over and over and over again, and seeing, do we get the same mass every single time? We would like to be able to get precisely the same mass every single time, but you're probably not. There's going to be some random error. There may be some air blowing through the room. It may be you may be breathing on it. You may have the scale not completely flat, which will create some problem. You may have more fingerprint. Every time you leave a fingerprint, you leave some fats and lipids and some protein from your fingers, and you leave them on the glass, which increases the mass. So all of these things we need to figure out how much error we can expect. And so if we can measure that amount of certainty, uncertainty with each individual piece of glassware. We know what our uncertainty is, and we know what the limit, or what we call quantifiable measurement. So one way we're going to figure out that the limit is by looking at the scales provided on each individual equipment. And if you look closely at the, I don't know if you'd be able to see this particularly, it doesn't really show up very well. But on the top, on the very top of the 10 mil graduated cylinder, it has 10 and then a colon, 0.2, and then below it, it says TC, TD, and 20 degrees C. So it has all that information at the right at the very top of the graduated cylinder. So we know that 10 stands for 10 mils. What do you think that stands for, the 0.2? Have a look at the divisions in between each 10, 9, 8, between each mil. What do you think the 0.2 stands for? No, it's not percent error.
Random error?
It's close, but look at the divisions. How many divisions are there between each mil? So there's the large line in between each mil, and then there's the short ones in between each large one. How many short lines are there in between each one?
10,
Not 2,
10.
not 10. Have a look. You need to look right at the, you should have your 10 mil cylinder in front of you.
5 ticks.
5, right. So what do you think the 0.2 refers to?
Oh, 0.2 for each tick. So it'd be,
That's right. It means each individual line in here represents a difference of 0.2 mils. So it tells you how many measurements there are on the cylinder. So it measures 10 mils. There is a division every 0.2 mils, meaning that there are 50 divisions up and down the cylinder. So it gives you an idea of the accuracy of your measurement, that you should be able to measure things within 0.2 of a mil. Now, these down here, TC and TD, probably not familiar with these. Those refer to, TC means to contain. So it shows you that this is designed to contain 10 mils, a maximum of 10 mils, again, with the divisions of 0.2 mils. And the TD refers to deliver. So you can measure, it will contain 10 mils, and then when you pour it all out, it will have delivered the same volume. So this is one of the one of the pieces of glass equipment that's designed both to contain something and to deliver something. Others are just for delivering, and some others are just for containing. And then, why is it so important that there's a temperature there? Why do we bother having a temperature?
So that you don't like melt the plastic.
No, it's not it certainly will melt at much higher than 20 degrees. What changes about liquid with temperature?
Its state.
Yeah, you need to change it a lot though, in order for it to change its state. That's true. If you go from 0 Celsius to 100, it changes from a solid to a liquid to a gas. But even just changing it by a couple degrees, what happens to a liquid? Any ideas?
Does it gain more energy or
It does. It does gain more energy. And what happens when molecules have more energy?
they
What happens to the movement of them?
they move at a higher speed or
They
like higher
do. That's right. They move faster. And when molecules move faster, are they closer together or are they slightly further apart?
closer?
When they move faster,
Oh, shoot. Farther.
a little bit further apart. So what would that affect? If molecules are moving a little bit faster and they move a little bit further apart, what does that
The
affect?
density?
Affects
Does it
the
affect-
density. Excellent. That's right. It affects the density. And it doesn't affect it a lot, but it affects it enough that it will change your measurement. So this is designed to hold precisely 10 mils of water at 20 degrees Celsius. That doesn't hold true at 15. It doesn't hold true at 30. So at 30 degrees, it's going to hold this volume is not going to be precise. And at 10 degrees, it's not going to be precise. It's only precise at 20. And so that again gives you some idea of some of the uncertainty there will be in measurement. And we're going to take that into consideration in our experiment today. So how do we figure out the uncertainty? Well, we looked the measurement we did a little bit earlier, as was mentioned. Someone estimated that it would be 6.75. Excellent. It says here most people would give that. So how do we figure out what the uncertainty is? So a simple way of figuring it out is what is the interval above that measurement and what is the interval below that measurement? So if there's a tick for every 0.1 mils, as there is here, with our 10 mil cylinder, there's only going to be a tick every 0.2 mils. So remember that when you do your calculation. So what we do is if we measure this as 6.75, the high interval, the measurement that we could definitely see above that is 6.8. The measurement we could definitely see below that is 6.7. And so we add those, we take the average of that, we add those together and we divide by 2. And so we could say that the uncertainty in our measurement of 6.75 is plus or minus 0.05 mils. And that makes some sense, right? Because like we said, there's going to be people who say it's going to be 7.3, 7.2. Some other people are going to be say 7.6, 7.7. And all that uncertainty is around 0.05 mils. So we can say that the uncertainty in that number is plus or minus 0.05. Okay. So basically, if you had said anywhere from 6.7 to 6.8, you would have been in the within that interval. That because that is the uncertainty in that measurement. So we would have confidence that this 6.75 is again plus or minus 0.05. No more than that, but no less than that either. So that's like basically the maximum precision we can expect from that particular measurement. Now, if we wanted to measure it more accurately, would we choose something with more divisions in it or with fewer divisions in it? If we want more accuracy,
More divisions.
more divisions, exactly. We would make this like, twice as tall and a little and narrower, that the cylinder would be narrower, and there'd be more divisions in between. So we could get an even more accurate value. And in fact, if we want to measure something more accurately, we wouldn't use this. We would use something else in order to measure that volume. But most of the time, for our purposes, plus or minus 0.5 mils is close enough. That's going to be more than accurate enough for most of the experiments that we're going to be doing. So what do we need? We need our scale. So we got our scale. We got two different graduated cylinders. We got the little one and we got the big one. Notice on the big one that it says, there we go. It says 50 on the top, and then colon 1.0 TC TD 20 degrees C. So again, it's to contain and to deliver at 20 degrees, but this time it has 1.0. Why is it 1.0 on this one and 0.2 on the 10 mils?
Because of the ticks.
So what are the ticks? What does each tick on the 50 milliliter cylinder indicate?
1 milliliter.
Right, exactly. 1 milliliter. So there's exactly the same number of ticks on the 50 and the 10. They both have exactly 10 ticks across them. But because this is 5 times smaller, each tick is also 5 times smaller than on the big one, 0.2 mils rather than 1. So we're also going to need a thermometer. That's going to be really important for determining the density of the water we're going to be using. And then we're going to be using an Erlenmeyer flask. That's the one everyone was looking for earlier. The 250 ml beaker. And then you should have 2 plastic cups. We're not even going to put anything in the plastic cups. We're going to be determining the accuracy of our scale with the plastic cups. Then we're going to be determining the accuracy of volume measurement with the cylinder, the little one, the big one, the flask, and the beaker. We're going to see how those the uncertainties vary depending on the particular piece of glassware we're using. So where do we start? So the first one is really, really straightforward. So we're just going to measure the mass of 2 different plastic cups 5 different times. So you turn on the balance, you hit tare, you let it stabilize to 0, measure the mass of the plastic cup, write down the measurement, and then do it 4 more times. So for a total of 5 measurements. What is someone's either eating or tearing up some paper, I'm not sure. So for each trial after that, then we're going to figure out what's the average mass of the cup. And average is represented by this symbol here, X with a line across the top of it. That's considered the average or the mean. And then we're going to figure out what the deviation is from that average. So by how much does each individual measurement change from the average? Then we'll determine the average deviation. So this stays the same, and each measurement may be slightly different. Measure the difference and then see what the average difference is. So if it's a little bit high or if it's a little bit low, we don't put plus and minus. We just want to know how far the measurement is from the average. So get the absolute value. Because if it's a little bit high and a little bit low, we add all those together and we'll get 0 uncertainty. and that's not true. We want the absolute distance from the mean. And that will tell us how much uncertainty we should expect from the balance. And it should be pretty low. Oops. Didn't mean to do that. Let me go back. Oh, there we are. Okay. So now we're going to figure out the determination of uncertainty in our glassware. So this is important to know because we're going to be using the glassware for the rest of the term. We need to know how uncertain our values are. So we're going to be looking at, as I mentioned, the 10 mil cylinder. Whoops. Please work. I love computers. They never fail to work. Why isn't? Come on. For some reason, it's now not letting me draw on the. Anyway, I guess I'll just have to. All right. So we're going to use the 10 mil cylinder, the 50 mil cylinder, the flask and the beaker. And we're going to try and measure a different volume in each one. So for the 10 mil cylinder, we're going to attempt to measure 7 mils. In the 50, we're going to try and measure 24. In the cute little flask here, we're going to try and measure 17. And in the beaker, we're going to try and measure 35. So what we're not going to do is take the 50 mil, measure up to 35, and then pour it into the beaker. That's not the point. The point is we want to see how close we can get to 35 mils using this. And you'll find out pretty readily that this is a really crappy way to measure 35 mils for the pretty obvious reason that what's on their 250 mil beaker, what's the very first volume on the side here? Hopefully you've got
50?
it out. 50, right. So there's literally nothing between 0 and 50. So you're going to have to eyeball what you think 35 is. And so for this particular example, what is our high interval and what is our low interval? 35. Using using the measurements on our 250 mil beaker. What's the lowest measurement and what's the highest measurement around 35? Reflected on this.
80. 80.
Or what's the lowest?
70.
What's the lowest volume we could accurately predict using this particular piece of equipment?
Just 50.
There it goes. Not really. No, not 50. Because
70.
we're going to be trying to measure 35. So
Oh, wait. Oh,
what's lower than 35 that we can accurately measure with this thing?
25.
Where's the 25? I don't see a 25 on this.
Would it be none?
It'd be 0. That's right. Our lowest example is 0. So our low interval is 0. What's our high interval?
Is it
50.
50, exactly. So when we're trying to figure out what our uncertainty for this would be, then our low interval 0 and our high interval is 50. What about with so for a 25 mil cylinder, a 25 mil flask, we want to measure 17. So what's our low and what's our high for this one?
12.5 and 25.
Yes, 12.5 is the low and 25 is the high. So basically the difference is 12 and a half divided by 2. So our interval should be around 6.3. So you're not going to, if you don't get, if you, attempt to measure 17 and you get actually like, 21 or something, that's really good because we're not expecting this to be very accurate. In fact, it's not designed for accuracy. It's not designed to be used as a measurement, to measure volume at all. So this isn't designed for measurement. This isn't designed for measurement. These two are. So we should expect our uncertainty in these two to be much, much less than the others. So how do we exactly do that? Well, we're going to measure the mass of each one of our 4 different glasswares. Then we're going to pour in what we think is the volume of water called on. And then we're going to put it on the balance and measure the mass. So we'll subtract the mass of the empty vessel, and what's left as mass inside the vessel will be the mass of the water. So how are we going to go from mass of the water to volume of the water? And we did an experiment about this just the other week. We took volumes and we converted them to masses. Then we did the opposite. What did we use to convert one to the other? Now, Ulysses, you're close. How do we know that 1 mil is the same as 1 gram?
Conversion. I mean, that equation on like something is equal to grams over milliliters.
What equation is that?
Ah, shoot.
Because it's going to be different for every liquid, right? There's only one liquid where 1 gram is equal to 1 mil. And that's water. So what is that a measurement of? What property is that of water?
Density.
It's density, exactly. So how are we going to know what the density is? Why are we measuring why do we need a thermometer? There's a thermometer in this particular lab. Why do we need it?
To see what the volume is at a certain temperature, because water has a density of, what is it, 1 at like room temperature, something like that?
Right. Water has a density of 1 at a very precise temperature, 1.0000. Now, the density is not going to change much with temperature, but it is going to change. And so we need, my determination of volume from changing mass to volume is going to be different from yours, depending on what the temperature is. And so we use this particular table. And so what this table gives us, can I finally draw on? No, it's just not letting me draw. I don't know why. Anyway, I will try. And so the way we use this particular table is that on the extreme left side, it has temperature in degrees C, right? And as we go across, it says 0.1, 0.2, 0.3, 0.4. That means at 18.0, the density is 99986 grams per mil. At 18.1, it's also 9986. But as we go across to like 18.8, it's 0.9984. So it slightly changes. So each time, so we need to measure the temperature of the water. Right now, I've got my thermometer directly in the water I'm going to use. Hopefully the temperature is between 18 and 25. If not, we'll have to look up the density of water at that temperature. If your temperature is below 18 or above 27, just look up what the density of water is. You can find that online. Okay.
Okay.
Yes.
What if like I get water from the water dispenser? Like that one usually comes out cold, or is that fine?
What I do is I've just, yeah, I mean, I got mine out of like, I have a little setup in the corner of the kitchen that obviously doesn't get a whole lot of light, so it's a little cool in there. So I would just want the temperature just before using it.
Okay, so should I like make sure that like it's at room temperature before I do this, or?
That would be best, but
Okay.
I mean, whatever the temperature is, because it's
Okay.
probably not going to change dramatically from. So basically, I'm just leaving my thermometer in there, and whatever the temperature was when I poured it into the whatever container, that's what I'm going to report the temperature as. So I've had it in here for quite some time now, and it's still only 7. So it's a lot colder than I would expect. So what I'm going to do is that I'm going to look up what the density of water is at 7.0 degrees, and that's what I'm going to use for my density. Same with you. So if it comes out cold, then either you let it warm up to room temperature, or just before you pour it in the whatever container you're going to use, get the temperature, and then you report that. Okay. Yeah, I'm really surprised the water's staying that cold. I would not have expected that. So this is our first table, is just measuring. This is determining the precision of our lab, of the balance of our scale. We put in the 5 masses. We put in each deviation from the average after we calculate the average. And like I said, it's always going to be positive. If it's less, report the positive value. If it's more, report the positive value, and then get the average. So we want to see cup 1 and cup 2 should be fairly similar. I mean, the uncertainty is, there's going to be a different uncertainty in the difference of mass between these 2 cups than there is the uncertainty of each measurement with the scale. So that's why we measure the deviation separately. And even if cup 1 gives you a certain average mass and cup 2 gives you a different average mass, the deviation should be similar in each case, because the uncertainty of the balance is not related to the what it's weighing. It's related to the uncertainty of the instrument itself. So then the second one, we just fill in the mass of the glassware empty. We pour in what our estimated volume of water is, 7, 17, 35, forget what the other one was. Make a note of what the high and low interval for the volumes are. Calculate the uncertainty. Calculate the mass of the water that's inside. And then we use the density of the water at the particular temperature that you're using it at to figure out what the volume is. And then finally, we're going to see which one is the most accurate. So what the mass of water is, what the temperature is, what the density is, and calculate the volume. So then we'll be able to calculate what you actually saw, what the actual volume is in here, versus what you measured the volume to be. So if you measured the volume to be 7, and you determine from the mass and then the density that you get back is like 6.95, that gives you an idea of how accurately this thing is at measuring volume, and how good you are at determining or using this thing. So some of the error isn't going to be due to this. There's some amount of uncertainty is due to this. The other amount of uncertainty is due to how you use it. So that could be seen sometimes as a systematic error. If you're constantly looking from above at the meniscus, if you're always doing it the same way, you're going to be making a mistake in the volume the same way. If you're always looking below it, you're always going to underestimate or overestimate the volume doing it that way. So that will also give you an indication of how accurate the instrument is and how good you are at using it. Okay, so any questions before we begin? As you can see, this is going to be a pretty straightforward lab and pretty, hopefully, fairly easy to do. The calculations, just as most labs are, you'll be spending more time doing the calculations than actually doing the experiments themselves. Any questions before we get started?
I had a quick question. So after the density lab, I actually threw away my cups. So
All of
can
them?
yeah, all 8 of them. Can I use
Yeah, use
these
something
small
else.
ones? Like the smaller ones that we have?
Sure.
Okay, cool. Thank you.
Yeah, no worries. Or, you know, if you got you probably got some plastic cups at home, right? You just need 2 of them to be relatively the same mass. Or you could
Okay.
use, basically anything that's less than 100 grams. Because I think this goes up to 100 and then stops. So coffee cups probably going to be too heavy, but if you had something less heavy than that, you could use that. Yeah,
Okay.
that's not a problem.
Okay, thank you.
Yeah, no worries. Anything else? All right, so why don't we, go ahead.
Oh, I was gonna say, I forgot my thermometer at home. I thought I put it in my box, but it's not there.
Where are you doing the experiments? If you're not at home.
At my friend's place.
Oh, cool. Does she have a baking thermometer?
She doesn't cook.
Oh my God, who doesn't have a baking thermometer in their house?
I don't.
Oh man.
And
How do you know when your chicken's ready?
I cook for her.
How do you know when your roast isn't overdone? You know, all this stuff. That's going to be tricky. Maybe you should just do it tomorrow when you're home.
Okay, because temperature, it has to
Because
be
the temperature
consistent,
part
right?
is really important.
Okay, I can't just do like one part of the like.
Oh, you can
activity
do
here.
the first part. Yeah,
Oh, yeah.
First
Okay.
part's fine, but yeah, the second part, unless I don't know, is there an app on your phone or something, or the computer, a thermometer?
I mean, can someone suggest an app for me, or I can download it like right off?
Yeah, I don't know of one, because I don't know if your phone has a thermocouple in it. It might.
Would she be able to use a what you call it, like the thermometer that you use to take your own body temperature, or no?
I don't think so.
Okay.
Because you need to make contact with that. And I don't think that works. I mean,
Like
you
when
can
you
try
put-
it. I don't think you want to
Okay.
get that wet anyway. So
Uh,
maybe if you put it, I don't know, maybe if you put it up to the side of the container, but then that's the temperature of the container, not the temperature of the water. So
mhm. Okay.
yeah, probably not.
Okay.
No worries.
Well, all right.
Yeah, like I said, this isn't going to take very long, so you'll be able to knock it out in just
Yeah, when I go home.
20 minutes when you get home. Okay. All right.
Okay.
Let's come back at 3 and we'll get started once you get everything all together. Okay. All right. We'll just take a little break. Okay, so let's get started. Best way to do this. I'm just gonna. Here's my scale. Turn it on. Now remember that the G, you want the G just for grams, since this thing measures grains and carats and everything else. So let it sit for a minute to get to 000. It's not moving. And when you put the cup on, you want to let it sit for a minute too. So when I first put it on, it was 10.19. And now it seems to have settled in. 10.22. Take it off, let it go to 0 again. Measure it again. 10.21 this time. Interesting. 10.23 the third time. $10.21. And 10.23. All right, so I'm going to hell happened there? Let's try that again. Okay. So I had, what is going on? Let's see if this works. Nope. I'm having trouble with Zoom today, it would appear. Let's try that one more time. Are you getting a black screen on your from me now, or a white screen?
Black.
screen.
Black, right? Yeah. Huh. So Zoom is being naughty today. Let's see if we share something else. Maybe I can draw on that. Let's see if this works. Now it won't let me draw on it. Oh, Zoom. Huh, maybe we can just type on it. There we go. More than one way to figure this out. So my first measurement was 10.22. My next one, 10.21. Next one was 10.23. Oops. 10.21. 10.23. See if I can move this. There we go. So everyone can see those numbers?
Yep.
Oh, cool. Yeah, there's more than one way to do this stuff. So those are my 5 measurements. So see what the average is. So just use my good old calculator here. Divided by 5. So my average is 10.22. So what's the deviation from each one? Oops. Let me go back here. So the deviation is 0 there. For the second one, it's 0.01. Third one, it's 0.01 also. Third one, 0.01 as well. And the last one is also 0.01. So 0.04 divided by 5. So my average deviation is 0.008 grams. So that would be my average deviation for cup number one. Now, so that's how you, so I can figure that my, each time I measure a mass of around 10 grams on my scale, it should be plus or minus 0.08 grams. So that's pretty darn accurate. And so I would expect the second cup, even if I get different masses, my average deviation should probably be fairly similar.
Professor,
Yeah.
how did you get the standard? I mean, the deviation from the one next to in the second column next to the 10.22, like the 0.01, 0.01.
Yeah, each of those is the deviation from the average. So each one of these numbers, each one of those is a specific measurement. And then the average is this. And so this is how much they deviate from the average. So the 10.22 didn't deviate from the average at all. It's exactly the average. So the deviation from the average is 0. And then each one of them, 10.21 and 10.23, they're all 0.01 grams away from the average. That's all that is. Yeah.
Okay, wait. So okay, so we're just taking whatever like leftover that is from the average, right? To get okay, thank you.
Exactly. That's your deviation from the average. And there's going to be some. I mean, it's very unlikely that you'll measure exactly the same mass 5 times in a row. I mean, if you do, you know, that's great, but that's probably not going to happen. So as I measure my second one, yeah, pretty much exactly the same mass as the first one. Oh, wait a minute. No, that's not true. So the second cup, man, it's really different. It's 9.83. Interesting. So the difference in the averages is going to be basically how much tolerance there is of the factory that produced these things, how much different these are from each other. Because I mean, presumably they were all made at the same time. I don't know if these were made at the same time, if these are in the same batch. I don't know how big a batch they make, whether these were from the same run. Don't know, but we'll see. .80. Yeah, there's a definite difference. The second cup is significantly lighter than the first one. All right, so for my second one, I got 9.83, 9.80, 9.81. Are people seeing a difference between the two cups? It's like this dramatic?
Yeah.
Huh. Trying to remember when I did this last time, if I saw this big of a difference. So what is my average? 3. 0 plus 1 plus 1. 5. So my average is 9.812 grams. So the average deviation. So what are my deviations? Two. 2. And 2. So actually my average deviation might be less this time, as we will see. Actually, pretty much exactly the same. Interesting. 0.0072.
Professor, I don't know, maybe something's wrong with mine. I got a negative deviation average and a 0.
Oh, no, you shouldn't. Yeah. No negative numbers. Notice that all my deviations are positive. So all your deviations should be positive. So even if the math, even if each measurement is less, if it's less than the average, you report it as a positive number. If it's more than the average, you report it as a positive number.
Oh, okay. Because like the second cup, like the average is 0 because I got 2 negatives, like negative 0.006.
Yeah, change those to positives and then redo your calculation.
Okay, thanks.
Yeah. Yeah, so this works out perfectly. Sort of, I was shooting my mouth off about even if your mass of the 2 cups are the same, the uncertainty should be or different. The uncertainty should be the same, and that certainly is true here. So the difference between 0.0080 and 0.0072 is pretty small. That's only a difference of 10%. So that's pretty small. All right, now I'm going to try measure the mass of my 10 mil cylinder.
For the high and low intervals,
Mm-hmm.
it's based on the like millimeters on the flask, right? So like for the 10 millimeter graduated cylinder, it'd be 0 and 10.
No, because there's a lot of marks in between 0 and 10. That would be the case if there's only like no mark. If there's only just one mark on it at 10, then that would be the highest and the lowest. But for instance, if you measured, so if with your 7.0, there's a tick above 7.0 and there's a tick below 7.0. Which one, what's above 7.0 on the 10 mil? So there's a long mark right at 7, but then above it, what is it?
7.1.
Well, look and see remember, what is each tick on the on the 10 mil cylinder. There's
Zero
5
point
ticks
two.
in every mil. So what one is just above 7? There's some way to put something dark behind this so you could see it better.
One.
But on your cylinder, you see the long mark at 7, and then there's one above it and one below it. What's the volume of the tick just above the 7.0?
0.2.
That's right. So the high interval is 0.2 greater than 7, and the low interval is 0.2 below 7. So 7.2 is the high and 6.8 is the low.
Okay.
Okay? All right, so measure this volume again. Oops, 0. And you can use the transfer pipettes to measure to put the water in your particular cylinder. Don't just try pouring it in there. It's just not going to be very accurate. So what I'm going to do is get one of my transfer pipettes and use that. Yep, so I got them in here. All right, John? What's up, buddy? Yeah, so I just transfer like this. So I'm not going to just pour it in there. Till I get up to 7. And again, I want to hold this right at eye level when I'm adding my water and make sure that there aren't any drops on the side. It's pretty much exactly 7. All right. So empty. (11.01 grams empty. And then full. 18.07 grams. The mass of my water is 7.06 grams. So now I need to take the temperature of my water, and it appears to be significantly less than the temperature of my water is 7 degrees Celsius. So I'm going to have to look up the density of 7 degrees Celsius. And my density is, wow, 99999. That's pretty close to 1. My density is 0.9 9999 grams per ml. Oops. So what is my volume? Well, shockingly, my volume is also 7.06 mils. Not a surprise. So I was expecting 7. So my error, 0.06 mLs. So we'll have a look and see how we're going to report that. So my low volume is 6.80 mils. My high volume, 7.2 mils. So my uncertainty is going to be 7.2 plus 6.8. Wait a minute. No. Let me do that again. Oh, my intervals, right. So they are both 0.2 away, like divided by 2. And that's how we do the measurement.
Sorry, I'm confused for the volume versus the mass of the water.
Oh. Where are we? What?
So the volume of the water would just be the measurement of it in milliliters?
Oh, where's my, what screen are you seeing right now? I'm not seeing any particular screen.
The one you've been typing on.
Yeah, well, I can't see it now. So wait, let's see if I can get it back up. There we go. Right. So the mass was 7.06 grams. And the density of the water, my water, at 7 degrees Celsius is 0.9999 grams per mil. So I just did the conversion of grams to mils, and I got the same volume, since 0.9999 is pretty much 1. So my error is the difference. So now I'm just working out what the uncertainty is. So the uncertainty is your high volume subtracting your low volume divided by 2. So 7.2 minus 6.8 divided by 2 equals 0.2. My uncertainty is 0.2. So basically what that's telling me is I should be able to measure the volume accurately within 0.2 mils. And you can see that I was able to, because my volume, my actual volume of water was 7.06 mils. So that's well within the uncertainty. So then our accuracy is in the last table. So my mass was 7.06. Current water temperature was 7. Density was 0.9999. And again, you want the units in here. This is not acceptable what I'm writing. So I calculated 0.076. So these are the questions that you'll have to answer afterwards as well. So which piece of glassware is the highest degree of accuracy? And then you have to justify your argument based on the measurements you're making, okay? So I'm gonna do one more. I'm gonna do the 25 mil flask. See what I get for that as another example. Is everyone still clear on the, for the cups, we want the absolute value of the deviations from the average? That's really, really important. $25.90. So my mass of my graduated, of my 25 mil flask is 25.90 grams. Oh, that's not the mass of water, never mind. Minus. Now, trying to eyeball what 17 is going to be pretty difficult. I think it's basically when you're trying to get 17 in here, basically all you know is going to be somewhere between 12.5 and 25. But the problem is that it's not the same shape. So trying to figure out if it was the same shape, it might be easier. You know, you pretty much go halfway up. But since it's not the same shape, that makes it even harder to try and figure out where 17 is going to be. All right, so I'm going to stop there. Let's see what I get. All right, 44.54 grams. So my mass of water oops. 18.64.
So for table 2,
Mm-hmm.
for the volume of water, it says in activity 2, number 9, repeat steps 1 through 8, which with each remaining glassware, use the target volumes listed in table 1 for step 4.
Mm-hmm.
So does that mean we just put 7 milliliters for the volume of water?
No, that's only the target for the 10 mil graduated cylinder. There's different targets for each one. The target for 25 mil flask is 17. The target for the beaker is 35. And what's the target? What's the target for the 50 mil? I don't have that in front of me.
24.
24. Right. So they're all slightly different. That's
is
in the
what-
instruction, that's in the lab instructions.
Yeah. So is that what we write in for the volume of water for each of the different ones?
For estimated, yes, for your estimated,
Okay.
yeah. Because that's what, I mean, you're estimating that is the volume in there. You're gonna try and get to that
Yeah.
volume. Yeah, but then you're gonna figure out what exactly the volume is based on the mass.
Okay. I got it now.
Yeah, so the mass of water in grams is gonna be awfully close to the volume in mils, since it's so close to 1.
Yeah.
Since it varies a little bit with temperature, we need to figure out what the temperature is.
All right. Thank you.
No problem. So for my mass of water for the flask, I got 18.64 grams based on that density. So the density is pretty much exactly 1. So I guess I can divide it by 0.9999, see if it makes any difference. I think it will. And it doesn't. Okay. So my calculated volume here is 18.64. So here, so for the 10 mil cylinder, my relative error is 0.06 divided by 7. So that is difference of only 0.86%, which is pretty darn close. That's really good. But I'm thinking that my percent error is going to be significantly greater this time. So 1.64 divided by 17. Yeah, so my relative error for my 25 mil flask is 9.65%. So you can see that the error in measuring volume with the flask is over 10 times greater than it is measuring it with this. So you can see why we use the cylinder for measuring volume and we don't use the flask. And I can imagine that the 250 mil beaker, the error is going to be even greater. So are there any questions basically on how to proceed from here? Have a look at the questions in the report template. And if any of them don't seem to make much sense or anything, let me know. I'm going to duck out for like 10 minutes and then I'll be back. So if you have any questions, we can talk about them and then wrap it up and call it a day. All right. See if I can figure out what's going on with not being able to write anything. Okay. Let me pause the recording.
I just had a quick question.
Sure.
Where do you find that number 3? Because I'm looking on like the page after. Oh shoot, the page after like the data table number 3, data table 3, and I don't see any like question down here.
Oh, what is that?
I printed out the PDF of the measurement and uncertainty, lab number 9 from Canvas.
Really?
Yeah.
Let me have a look at that. It's possible there's maybe an old version. And if it is, I'll put the new one in there for you. Because yeah, there's definitely some questions to answer. Report templates, lab number 9.
I think the one you got is from the instructions, not from the template. The tables you have. because
Oh.
the report is a
Oh, no,
different-
they're in there. There's questions in there.
Yeah.
Where do I go to find the template one?
They're under templates rather than instructions. They're named the same thing, so it's kind of confusing. That's what, yeah.
Yeah, so it's lab report templates and safety. It's below the lab instructions, and the lab report templates are in separate. Here, let me share the screen with you.
All right, thank you.
I'll go to student view. Of course, hopefully all these things are on student view as well, because if they're not, then I'm in big trouble. All right. Share screen. All right, so hopefully you can see the Canvas page.
Mhm.
You see it? All right. So I'm going to scroll down to remote lab instructions. Where's the remote lab instructions? So all of them are listed there. So we're doing number 9. So those are the instructions that come from the company, like how to do the experiment. And then the report is just below it. Lab report templates and safety. So you open that one up, and I scroll down to lab number 9, measurement and uncertainty.
Oh, okay. Okay,
So
I
that's
got
one
it.
in there. So there's 4 pages, where you put your name, the date. There's the tables. You see, man, I've made it so easy for you guys. You don't even have to have I've even given you the title for the data tables. I shouldn't have put that in there. And then these are the problems below. So you
Okay.
put your answers below. And so not only do you have to give an answer, you have to explain your answer. That's the key. So, would you expect the average deviation if you did another cup from the same run? Would you get the same mass? Would you get a different mass? Would the deviation be the same? So that sort of thing. And then for number 2, which piece of glassware is the highest degree of precision? Explain why that is. And then number 3, which one is the highest degree of accuracy? And then you have to give like numerical reasons why that is.
Okay.
Okay.
Okay, thank you.
All right, no problem.
For the data table 2,
Mhm.
we
Let me-
add 7 millimeters of water to each of the different like graduated cylinder, the Allen.
No, there's a different amount for each one. And
Oh, that's the 24 millimeters, 17 and 35.
right, that's in the instructions. So in
Okay.
the instructions, do I have the instructions open? Hopefully I have the instructions open. Yeah, so, oh, here they are. Yeah, 7 mils for the 10 mil cylinder, 24 for the 50, 17 for the flask, and 35 for the beaker. Yeah. Because I mean, it'd be basically impossible to try and measure 7 mils in a 250 mil beaker. I mean, if you were within like even 100%, that would be a miracle. So yeah, 35, at least you have a fighting chance of getting right. And then basically we want to see if your accuracy is within the uncertainty you calculated. In fact, I should have asked a question about that, which I will do next term.
The only one that doesn't have like the measurement that tells you about the deviations in the line, or like the little lines. You know how the graduated cylinders tell you like 0.2 or 1.0, but the beaker doesn't.
No, you have to figure that out yourself. So here it doesn't, yeah, on the beaker, it doesn't say what the ticks are. So you have to sort of figure that out. So there's 5 of them in between 50 and 100. So each one of these ticks is 10 mils. But you are measuring less than 50. So the interval that you can actually see on this beaker that's below 35 is actually 0, because there's no interval below 35. There isn't any.
Yeah.
And the only interval above 35 is 50. So for this particular example, your high interval is 50 and your low interval is 0.
Okay.
So your uncertainty is going to be pretty high. Your uncertainty is going to be like 25 mils. So
Yeah.
basically what we're asking you to do is, can you measure 35 mils plus or minus 25? So that's a big range. You should hopefully you should be able to get in there. But you can see why we don't use that as a way to measure that volume.
All right. Thank you.
No problem. All right, I will be back in a minute and then we'll wrap this up. Let me pause. All right, so how are people doing so far? Did you find your relative errors for the two cups were pretty similar? The average error or deviation? Maybe you haven't done the calculations yet.
Okay, can I just say something? I just got like for the how do you call it? And how do you pronounce the name of this flask? I don't know.
That is a
17
Erlenmeyer flask.
Erlenmeyer flask.
You'll never
got-
guess who actually developed the Erlenmeyer flask. Take a wild guess. Go ahead.
I got a 17.77 ml.
Oh, that's fantastic.
Yeah.
That's really good. Yeah, I had someone last term get it exactly. They got exactly 17. And so when they did their calculations, they said this was the most accurate thing to measure volume in. And I couldn't say they were wrong because their percent error was 0. So it's like, yeah, okay. But yeah, that's really good. 17.8. That's excellent. That's much better than I got. Yeah, mine was way off. I had like a 10% error on mine. So anyone else have any questions? Okay. Everyone's crushing it. Steven's crushing it. That's the main thing. All right. So if you have any questions about how to do the calculations or how to write the report or anything like that, just come on. Just send me a message or Jerome here. He's not very good at responding to email messages though, because his reading aptitude isn't what it used to be. All right, everybody. Good luck. I'll talk to you on Thursday. Remember, I have office hours tomorrow at noon if you want to drop by and ask any questions then as well. Okay?
Bye.
All right. All right. We'll talk to you soon.